They, Lieven will talk about all this super nice history and physics and exciting future of the field. So Lieven, thank you very much for giving this presentation.
Well, thank you, Christian. Yeah, thank you, Christian. Yeah, this is a talk that I've been thinking of giving for quite some years, and finally I'm doing it. So I'm very happy, and also I think this is a perfect occasion, the QuTech360. You already mentioned how I planned to start. 25 years ago, and as I was working on the last year of my PhD, together with Matthias Steffen, who started the year after me, we were able to factor 15 using 7 spins in a molecule. 7 of the spins in red had a spin 1/2 nucleus. The other nuclei were either spinless or had high spin and didn't interfere. And we sent a sequence of more than 200 radio frequency pulses to these 7 spins, each of them carefully tailored in amplitude profile, in phase profile, accounting for all the crosstalk, in order to arrive at the fact that 15 is 3 times 5. So that was the crown of my PhD on 4 years of hard work. And actually it was quite fun. I think we learned a lot. But one major downside of this approach is that we operated at room temperature. And at room temperature, a nuclear spin, even in a large magnetic field, has almost 50-50 probability, almost equal probability for being in one spin or the other spin state. So that's not a good way to start a computation if you're building, well, in general, and also another quantum computation. What you need is a system that's properly initialized. The reason why we could still do these experiments and run the algorithm is we could make the signal such that it was proportional to the signal from a ground state molecule, all the spins in the ground state. The catch is the proportionality factor goes down by a factor of 2 for every spin that you add. So there is an exponential cost. It's of course not what we want in quantum computing and not a good strategy. The other is, this was done on many copies of this molecule in liquid solution. Let's say Avogadro's number of copies. It was a glass sample tube, so it was basically a liquid computer. All these molecules were tumbling around, and we were averaging these spectra over all of the molecules in the solution. And so, at the time, I was really motivated to move to individual spins and quantum dots. And it's actually interesting to also put this in perspective, right? So all of us are now working with individual quantum systems every day. It's routine at QuTech. But certainly, it certainly wasn't routine half a century ago, or let's say 1950, when it was not even routine, but even thought to be completely impossible, like science fiction. This is a quote from a paper that Schrödinger wrote, comparing how hard it is to control and measure single particles, single atoms, electrons, photons, with raising ichthyosauria in a zoo. Well, it's presumably hard. I don't know, raising ichthyosauria. I think that's what he implied. Okay, now, indeed, I came to Delft to work on semiconductor quantum dots in the group of Leo Kouwenhoven as a postdoc, and together with 3 PhD students that were already working here, Ronald Hansen, Jeroen Elzerman, and Laurens Willens van Beveren, we started to work on building quantum bits from single electron spins. And I have to say, a bit naive, coming from NMR, how hard can it be, to rotate a single electron spin? It's a 2-level system. You apply a magnetic field, you'll get a frequency splitting. You apply an oscillating magnetic field, and for sure it will rotate. Why not? So how hard can it be? Well, okay, if you're in 2001, the first question is, how do you isolate a single electron? At the time, there were single electron devices from Terruccia. They were so-called vertical quantum dots, but they weren't quite suitable for building quantum computers from them. The lateral structures that we called them at the time, which we now know as sort of these gate-defined, devices that we all use, looked more promising, but we had to learn how to isolate single electrons in those. It wasn't possible at the time. Next, how would we detect the spin state of a single electron? Now we do that all the time, but back then we had to come up with the ideas and techniques for doing that. And also, even delivering the control signal, I said, well, apply an oscillating magnetic field, the spin will rotate. Okay, but you have to do that in such a way that you do not also and intentionally have oscillating electric fields that may kick out the electron from the quantum dot, or that you avoid too much heating and so on. So it wasn't trivial. It didn't look trivial, and it wasn't trivial. So through the talk, I'll discuss these questions and then how we resolved them over the years and what we learned. I started collecting slides, and initially I planned to also include work from other groups, but even covering what I wanted to share from our own group was more slides than fit in a talk. So a disclaimer: I will say very little about parallel work in other groups. I'm also going to focus mostly on the work that we did here longer ago. It's equally interesting for sure what we did in the last 5 years, and we learned lots, and I'll briefly flash some of it for completeness. But all of you here are more familiar with it and less familiar with the old stuff. So that's why I focus on that. And then last disclaimer, you will see slides like in preparation and unpublished and so on. And I on purpose left it like that. There are also some statements which I now would revise, but I also left it on like they were at the time, sort of to share how we were thinking throughout these years. So starting with how to isolate individual electrons. This is the device that we used and that made it work. We called it after a Japanese cartoon character, I believe. Do the Japanese people recognize it, or is it from longer ago? Yeah. So Gundam, and it combined two concepts that had been introduced by other groups. The difficulty with isolating single electrons is the following: you kick out electrons one after the other by making the gate voltages more negative, but then you also tend to make, for instance, here you tend to make the barrier more closed, and at some point you may have one electron, but there is no more current flowing through that would allow you to detect the electrons. So that was a challenge, and so this open design from the Sakraida group solved this, and we copied that for a double dot. And then the other is that you see here quantum point contacts on the side. We copied that from the Heibloom group. This allowed us to detect the number of charges without relying on current flowing through the quantum dot. Because, like I said, if you rely on the current flowing through the quantum dot, the current gets pinched off. You see that here, as you're familiar with Coulomb peaks. Every time there is a Coulomb peak, the number of charges changes. In this case, changes down by 1. And then, here there is the last Coulomb peak. And then if I would tell you, so here the dot is empty, nobody would believe me because you see a large peak next to a tiny peak, and then, what's there? Yeah, maybe there are more peaks, you just don't see them. And in fact, it's true. There are more transitions. You can detect it in the point contact, a step, corresponding to individual charges leaving the dot. And then after this last step, you don't see anything anymore. And so this is how we knew that we could go to the last electron. Well, actually here it's empty, and then you go back. This is now routine, of course. We do this every day. We also felt we wanted to somehow see our spin in spectroscopy. This was a big thing. Can we see the Zeeman splitting in spectroscopy? If you're taking Coulomb diamonds, so you measure the transport through a quantum dot at large source drain voltage. As you open the window and excited states enter the bias window, you will see increases in current, and that happens here, for instance. And so as you apply a magnetic field, do we see that these lines split? This also was the first time that we did this or could do this. The reason is that, what was necessary is to reach this clean regime where we had just one electron, and then you have a very clean spectrum, ground state, excited state, and both of them split. And the splitting increases with magnetic field. This was already a first mini surprise. The splitting doesn't increase linearly with magnetic field. Right, so this is what you expect for the bulk gallium arsenide G-factor, but it actually kind of fell off. I will maybe skip over the reasons for that now. Okay, so we can see the spin in spectroscopy. The ground state and here the excited state enters the bias window. And so Hans-Urs Engel and Daniel Loss had proposed then how to use this capability to also detect that we could achieve spin resonance. And simply put, now you go to a regime where you're in Coulomb blockade, but if you manage to flip your spin, then the spin can leave the dot and another will enter. If it enters in the excited state, it goes through. If it goes in the ground state, you get stuck until you hit the resonance again, and then you take it out. And so, they predicted that next to the standard Coulomb peak, there would be sort of a side peak that would allow you to probe in transport that you've achieved magnetic resonance, right? By the way, if I'm going too fast or something is unclear, don't hesitate to ask. In order to make this happen, we of course realized that you would need these two lines to be separated by more than their broadening, more than temperature and also the tunnel coupling. And so in practice, we were aiming at fairly high splittings, let's say 30 gigahertz or more, which could be done, but okay, that's what we needed to do. And also we estimated, we didn't at the time understand very well the decoherence mechanisms. We were reading papers that we barely understood from Merkelov, Efferen, and Rosen. Actually, that was the one we understood best, but others we didn't understand so well. So we weren't quite sure what to expect in terms of T2 star. But okay, we aimed at Rabi frequencies of a couple of megahertz, which would mean about a millitesla in drive field. Yeah, that's a bit elaborated on here. Maybe I'll not say more. Oh, yeah, no, so one thing more. So if you aim at a millitesla, you can imagine different ways of doing this. And one of the ways that I did some back of the envelope was to build a microwave cavity. And the back of the envelope to me suggested that there would be too much power dissipation in the walls of the cavity and that your system would heat up before you reached the millitesla that we targeted. The Ensley group tried it, actually. They built a very special cavity with a lot of creativity in how they designed it, but yeah, that never really worked. So instead, we decided to go for a conceptually very simple concept. Well, conceptually simple concept, yes, idea. Basically send a current through a wire, and then from Ampere's law, you'll get a magnetic field. But okay, if you imagine a wire that's 200 micron away, to produce a millitesla, you need an ampere. That's a lot, at cryogenic temperatures. So clearly the wire needed to be very close. If it's 200 nanometers away, you need still a milliamp. Not that little, but okay, maybe in reach, we thought. And so we had the first design. This is actually still a single dot, as you can see, and we passed some current through what was supposed to be this wire. So we would get an oscillating magnetic field at the dot location. And this is what we saw. And there are side bands, but they're present on both sides. It's impossible to tell if we're driving the spin or not. Instead, what is happening is that unintentionally we apply or we generate not only an AC magnetic field that should drive the spin, but also an AC electric field. And if you have an AC electric field, it can take your electron out of the quantum dot. It just kicks it out. It's called photon-assisted tunneling. We also had evidence of pumping currents, charge pumping currents. Basically, if your drive, pushes your source and drain up and down in certain ways, you can also get currents through your device. So yeah, we were kind of struggling to dissect that, but we concluded that we really couldn't use this as a method to verify that we achieved spin resonance. And so the two ideas that changed this, and none of it is super deep, but we had to come up with it at the time, are two things. Very simple. To avoid that your electron gets kicked out when you're driving it, you'd pull it deep into Coulomb blockade, right? So this scheme from Engel and Loss, where you're close to the edge of Coulomb blockade, we wanted to avoid. We would pulse down, apply the drive, and then pulse up for readout. That would be one idea. And this is essentially the idea also of Elzerman readout, which we did in 2004. But then there was another idea based on work from the Tarucha group, where they introduced the concept of Pauli spin blockade, right? And so I think many of you know if two spins are in a spin singlet, they can come together on the same orbital. If they have different spins, one of them has to go to a higher orbital, and then you can create a situation where your current through two dots in series is blocked if the two spins are aligned, and the blockade is lifted if the spins are in a singlet. What's nice about this technique is that it can operate or detect spins even at very low spin splittings. You no longer need a Zeeman splitting that is much larger than your thermal energy, than the smearing of the reservoir. And so that was interesting. And so basically what we ended up doing is to combine these two concepts, combine pulsing and Pauli blockade. And here you see a bit more information on the hardware for how we did this. This is a similar device image to what I showed you before. Well, for clarity, I didn't mention it explicitly, but back then it was all gallium arsenide, no silicon or no germanium. So gallium arsenide was the workhorse of mesoscopic physics. So it's a heterostructure, gallium arsenide and aluminum gallium arsenide on top. You get a two-dimensional electron gas, and with the depletion gates, you form the quantum dots. Here you see this sort of clumsy-looking wire. It's barely a wire. It's just a coplanar waveguide, or coplanar strip line rather, that is shorted. And the idea was where there is the short, there will be a maximum current and a minimum in the voltage swing. This is how it looked zoomed out. What I couldn't find a picture of is how we were able to contact this strip line. We spent a lot of time on it, and we were very worried about having a good transmission onto the chip. In the end, we ended up using so-called pico probes. Maybe some of you have seen this. It's basically a coaxial line which has a special termination that has sort of flexible pads that can land on your chip. And we had one. They were expensive. We had one or two, but they had 3 contacts. So it was meant for a coplanar waveguide, and we only had 2. So Frank Koppens actually, by hand, manually cut off one of them, and then the other 2 landed on the chip. And this was going to be kind of an experiment to try and learn a bit. But it turned out that this actually, became the Koppens paper. Here you see some early results where, as a function of magnetic field and frequency, we plot the current, right? And blue means there is Pauli blockade, no current. And then bright is where there is current. So you see there is current at 0 magnetic field. That is because at 0 magnetic field, if you start in a triplet, which would be blocked, the nuclear spins will quickly mix it into a singlet. It's true for all of the triplets. They're close to, they're at the same energy. And so you get lifting of the blockade. And then you get the 2 side peaks, and of course, or side wings. And that's, of course, what we were hoping for. And this told us that we were hitting the resonance. The slope corresponded to the right, to the expected G factor. So that was good. There is more to say about it, but given the time, I'll not do that. Here is some early Rabi oscillations. So what we needed to add here was to also So here we then combined this concept of pulsing a bit more. And so, you begin to see sort of the Rabi oscillations. Later, they became a bit nicer. These are the published figures. If you look closely or even not so closely, you notice some things about the line shapes, right? What we expected would be a narrow and Lorentzian line shape. How narrow? A couple of millitesla. That's sort of what the nuclear field would do to the resonance frequency. You would broaden it by a couple of millitesla. But look at the scale. This is certainly more than a few millitesla. And it's also nowhere near a nice Lorentzian line. It looks kind of ugly with kind of steep edges, and then something on the top, I don't know. And then looking at this scan here, what you noticed perhaps is that it has sort of extensions that run upwards. In this case, we scanned the frequency upwards, and so somehow you get a very asymmetric line shape, and that is much, much broader than we expected. So what's happening here? Well, to us, this was indicative of nuclear spin polarization. And the thinking is that if you're driving spin resonance, you're exciting your electron spin, and if it's excited, it can relax back. And in doing so, there can be some interaction with nuclear spins, and you could, polarize your nuclear spins over time. And so maybe there was some buildup of nuclear polarization. That seemed plausible, and I'll come back to that. Actually, is it clear to you why a buildup in nuclear polarization would extend the line shape? Or, so please ask questions, right, if things aren't clear. So the thinking, but maybe I have it on the next slide. I'll answer that in a moment on the next slide. Here are the published Rabi oscillations. I can tell you we were super happy to see them at the time. First ESR on a single spin in a quantum dot, at least, and so we could also tell from these measurements that we actually produced a 2 millitesla almost drive, so that was good, a bit larger even than we thought. The Rabi frequency was linear in the current that we would supply to the drive line, so that seemed consistent. So many things are good about it. But of course, the oscillations quickly decay, and yeah, nobody wants to build a qubit that looks like this. But okay, you have to start somewhere. The decay is not only well, maybe I'm going to skip through this. There's so much to say, and I took out many slides, but the shape of this decay we studied in quite some detail, also together with the loss group. There is also a phase shift. But let me turn to these extended tails. And if we scan the magnetic field to the right instead of the frequency upwards, the tails could be even much longer or more extended. It's kind of crazy, like how can this happen? And so the thinking was that if you polarize the nuclear spins, then a majority of nuclear spins will point in a certain direction, and through the hyperfine coupling, they add a Overhauser field, an effective magnetic field, on the electron spin. And so the resonance frequency of the electron spin now depends not only on the external field that you apply, but also on this collection of nuclear spins that together produce a nuclear field, as we called it. And so that actually keeps us on resonance. But okay, that's still curious, right? Because somehow the nuclear field must build up, nuclear spins must be polarized at exactly the right rate to maintain resonance. So why would that be? And will we still be on resonance if we sweep more slowly or more quickly? Well, we tried this actually before I go there. To verify that it was really nuclear spins coming in here. We then also applied RF at the expected nuclear spin frequencies, and indeed we could see that the ESR response showed was modified when we hit the resonance frequency of each of the 3 isotopes of gallium and arsenic spins. So that was nice. But this one is pretty cool. So, sweeping to the right, you get this long tail. Sweeping to the left, you don't. And we then tried, a few more things. So what if we sweep the field past the resonance condition and then hold it fixed at this value, which is nominally absolutely off resonance. We should not be able to rotate the electron spin at this magnetic field. But, well, we still see that the spin is on resonance. So the nuclear field somehow stays at this fixed value. Okay, let's take it a step further. What if we sweep our field back and forth, starting from this condition? And then, well, maybe in some cases you lose it after a minute. In some cases, after 2 minutes, you're still on resonance. So this was quite interesting, actually, quite remarkable. And we understand, yeah, I think we have a good picture of what's going on here. So let me explain that. The graph you're seeing is on the horizontal axis, the nuclear field, and then here the rate of change of the nuclear field. And if you do nothing, then the rate of change should be this line, meaning the farther away you are from unpolarized. So this, I said it before, nuclear spins despite the magnetic field, even despite the low temperature, the equilibrium state is pretty much unpolarized. It's here. Tiny amount away from there, from zero. Okay. But if you're somehow manage to polarize the nuclear spins and build up a nuclear field, and then let it sit, it will return to equilibrium. So if you have a negative nuclear field, you'll get a positive rate of change that takes you back to the equilibrium value, same here. Now add on this electron spin resonance. And when you apply a certain frequency in the presence of a certain value of the external magnetic field, there will be a value of the nuclear field that takes you to the resonance condition, right? So this you fix and that you fix. And then there will be some nuclear field that takes you to resonance. Let's say it's here. And a priori, we don't know in which direction the nuclear spin polarization will be modified, maybe upwards, maybe downwards. In principle, agnostic a priori, if you don't think too much, but it's going to be something. Let's say it's down. If it's downwards, then you'll get a peak here where locally the nuclear polarization has a dynamics that is not just that given by equilibrium. There is something else going on. And if that's the case, then you'll find a second stable point next to this one. Why is it stable? Well, if your nuclear field happens to wander off a little bit to a lower value, immediately will be pushed back to this value, and the same coming from above. Right? Of course, you can only take it so far. This peak has a certain amplitude, and if you take your nuclear field beyond it, you will no longer have this second stable point. And also on the other side, you would not have a stable point consistent with what we saw. Okay, this is interesting. And in fact, what we demonstrated and explored a bit further, I took out the slides to elaborate, is that the stable point here is, there is a tighter restoring force than in equilibrium away from resonance. And so that actually meant that this allowed us to suppress, to some extent, the fluctuations of the nuclear field. So it allowed us to get a longer T2 star. Okay. Yes, please. The slope is the relaxation rate of the spins. So the question was, can we tilt the slope? And the slope is the relaxation rate. It depends a bit on temperature and maybe a bit on magnetic field, but in practice, we couldn't really, we didn't attempt to vary it. No. Okay. So this was the first part of the talk about electron spin resonance and what we learned about the nuclei. But also very early on, actually the year after, well, in 2007, so 1 year after the Koppens paper, with Katja Novak, we tried to drive the single spin electrically, which is now, of course, done a lot, especially in germanium, where there's strong intrinsic spin orbit coupling, in silicon with engineered spin orbit coupling from the micromagnet field gradient. But the thinking is that, yeah, this doesn't look like something that will scale well. Can we not drive the spin just by applying excitation to one of the gates that's already there? And by then we understood a bit how relaxation worked. The electric field from phonons will couple to the spin. So maybe the electric field that you apply on purpose can also drive the spin. And so we tried that. And in my recollection, this actually worked relatively straightforwardly, not too many puzzles initially. So, we saw the resonance, we saw a resonance frequency, and it varied linearly with magnetic field. We could see Rabi oscillations. Again, they're not fantastic if you look at them critically, but we were super happy to see them back then. Rabi frequency scaled linearly with the drive. So this is good. This seemed to work. And it showed for the first time that you could drive these single spin quantum dot spins electrically. And that's, of course, can be beneficial for scaling. It's more practical to get electrical signals, AC signals to the dots than magnetic AC signals. I have to say, when we did this experiment, we didn't understand yet very well or in detail when starting it, in what direction the motion should be, in what direction the external magnetic field should be, and it really matters, right? So you know that in a simple picture, if you displace an electron in a semiconductor, spin-orbit interaction acts on it, and it will introduce an effective magnetic field. If you move it in the other direction, the effective magnetic field will be opposite. Now, if you want to use this to drive spin rotations by going back and forth, it's a simplified picture. It's not completely accurate, but okay. It does matter in which direction you're moving, and it does matter that the effective magnetic field will be orthogonal to the static magnetic field that is needed for magnetic resonance. If your AC magnetic field is parallel to the static field, you will not rotate your spin. And so it turns out that we were lucky. Without thinking much about it, in this sample, we had the right alignment, and we could drive these rotations using spin orbit coupling. There was a parallel experiment from the Marcus group, and they tried the same experiment, and they only could see sort of the resonant response, but no Rabi. And it turned out they also had not thought about it, and they were unlucky. And they could only get a weak response, not enough for Rabi, but they could still see the resonance. And that resonance you would see not only if there is spin orbit, which in this case, for them was very small or absent, but you could also get the resonance by, again, the nuclear spins that come in. So the nuclear spins can also, in a simple picture, provide a field gradient, or in a microscopic picture, you can have a transfer of angular momentum between the nuclear and electron spin, and then the electric field provides the energy. You could also say we've had discussions about the role of luck in my group some years ago. you could also say that all of us weren't lucky or unlucky, but or sorry, well, I guess we were lucky and they were unlucky. But you could also say, I'm also convinced that you could also make your own luck. In this case, if you had thought about it carefully in advance, you would design your sample accordingly, and then you would make your own luck. So there is also an art to that, and I'll still admit that we were lucky. All right, and then of course there is the much used technique for driving spin rotations in silicon, for instance, or other materials where intrinsic spin orbit coupling is weak, where you use a micromagnet field gradient, and then you oscillate your electron in a micromagnet field gradient, and this will allow you to drive spin rotations. Now, by that time, we were doing experiments that, at higher magnetic field. I think maybe in some cases we also, used Elseman readout, no longer Pauli blockade. And then something else happened as we went to larger magnetic fields. When you're at larger magnetic field and you don't know your G factor precisely, I showed you how it depends on magnetic field, and there is some sample-to-sample variation. So we didn't know it precisely in advance. So you have to hunt for it. You have to hunt for the resonance condition. And at large magnetic field, a tiny uncertainty in G factor can mean you have to scan over a large range. And your resonance frequency is fairly narrow. So are you going to miss it? How long does the sweep take, and so on? So we started doing adiabatic chirps, so adiabatic inversion. So you chirp the frequency over a larger range, hoping to somewhere pass through the resonance condition, and that will invert your spin. And so that's what we did. And when we applied these adiabatic chirps, we saw, again, wildly asymmetric line shapes. In this case, it didn't depend in which direction we would sweep, and also not whether we would sweep the frequency or the magnetic field. I mean, it mattered a little bit, in the details, but the overall pattern was pretty persistent. And so it turns out that what is happening here is that we were seeing different mechanisms at play. We could either, so also this range here, that is the chirp range. And so somewhere in that chirp range, you hit the resonance condition if your drive mechanism relies on spin orbit coupling. But if your drive mechanism relies on nuclear spins, so the nuclear spins, provide the angular momentum and allow you to flip the spin. And in that case, your resonance frequency is a bit shifted, because your electron gets energy, but the nuclear spin takes some energy. So it's slightly shifted. And how much it's shifted depends on which isotope of gallium or arsenic you interact with. And so that allowed us then to understand this broad sideband. So yeah, lots of fine details in these measurements, and there is much more that I left out. All right, so this wraps up the gallium arsenide days. Here is an early group picture where you see Frank Koppens, Katja Novak, Ivo Vink, Tristan Meunier, many of you know, and Han and Tite were master students working with us at the time. So I have to admit, and it's not a secret for many years, but maybe 15 years ago, when we were only seeing gallium arsenide results, we were scaling up and so on, trying to build triple dots and quadruple dots. But I was also thinking about what shall I do after I stop working on spin qubits, after the field dies, because in gallium arsenide, the coherence was so limiting that I couldn't really see it go to a real technology. Of course, we knew from the beginning that if you could build dots in silicon, we would be in a much better position, because in silicon, only 5% of the nuclei carry a nuclear spin. Coherence should be much longer lived. You can even reduce the 5% to some smaller number by isotopic enrichment. And so this was known from the beginning, from the early 2000s. But for many years, it was a struggle to make suitable quantum dots. So in Sydney, for instance, Bob Clark and later Andrew Zurek and colleagues used silicon MOS. They were quantum dots. They were not well behaved. They were not stable and so on for many years. Mark Erickson on silicon germanium tried it, Hongwen Zhang at UCLA. It was difficult to make quantum dots that were stable and useful. But over the years, the quality of these dots improved. And when Menno came to UNSW and made the final push in these improvements, he observed these magnificent oscillations. Look at this. This is really stunning, right? Comparing to the gallium arsenide Rabi oscillations that I showed before. In this case, what made it so stunning is that it's not only silicon, but it's already from the beginning the isotopically enriched version of silicon. So it was 800 ppm silicon 29 remaining, and beautiful Rabi oscillations. We were working in parallel together with the Ericsson group on silicon, germanium. We only had access to natural silicon at the time. Now that's of course different, and thank you, Giordano. But at the time, this was not available. But we had our own effort, like I said, together with the Ericsson group. In the beginning, it was also frustration. We measured some dots, and by the time that you would go to the one electron regime, something would switch and you would have to start over. So we couldn't get anywhere. But at some point, the devices improved. I skipped the details why. And Erika and Pasquale saw a resonant response when applying a oscillating electric field. This was with a micromagnet. And the resonant response showed a G factor of 2. So this looked like, okay, we found spin resonance, we're in business, you know? So we thought. The line shape was not maybe as narrow as expected. It was also not much broader. The dephasing time, that we extract was fairly short, but yeah, maybe still fine. But the big problem is we couldn't see any Rabi oscillations. And they tried for some weeks, and I do remember, I'll also share this anecdote, that at some point I told them, okay, I'm not sure what's wrong, but let's warm up and think of something, start something else. This is not working. And fortunately, they didn't listen right away. And at some point, they moved the magnetic field. This was taken at 850 millitesla, and then at 560 millitesla, suddenly there was a chevron pattern. And so we were seeing Rabi oscillations, and of course, that was exciting. But there was something funny about it. Well, several things. When we took a Ramsey experiment and would vary the phase of the drive over 360 degrees, we would see 2 periods of Ramsey fringes. That's not supposed to happen. Any guesses? Not valleys. No, okay, I will not delay things too much, but we discovered that it actually was a 2-photon process. And when we halved the frequency doubled the frequency from 6 to 12 gigahertz, we saw the expected Ramsey interference. And so what was going on? It's a very funny story, actually. And yeah, maybe this was, again, a bit of luck and making your own luck by not listening and so on. But in the beginning, we saw this response. It had the right G factor. But as it turned out, in addition to flipping the spin, at this frequency, you also flip the valley. And that was not very coherent, and that's why we couldn't see Rabi. That's the thinking. At some point, they moved the lower magnetic field, and they came here, where the resonance intersected with a 2-photon pure spin transition. And so without knowing it, we hit the single spin transition, but then a 2-photon version. And then after doubling the frequency, we also found the single photon version, and then we had an understanding. So this was kind of interesting how that unfolded. Well, if we had gone up to instead of, 13 gigahertz or so, we would have gone to 20 something, we would have found it. Yeah, we should have found it. But somehow when we started, we somewhere found a resonance, and then we thought, we're on it. And then, yeah. Yeah. Oh, sorry. So the question, yeah. So the question basically is, if we had been completely agnostic about where to expect the frequency and had covered a larger scan, would we have more quickly understood? And I think so. Yes. Yeah. So yeah. But okay, these scans are lengthy, right? And especially back then they were lengthy. Because yeah, the single shot cycles were not nearly as efficient as they are now.
But that's down to 0 field. You would not be at 0 resonance frequency. Is that something you noticed then already, or?
Yes, and it was in the slide, I think. Very good question. Offset from micromagnet. Yeah, that was the thinking. No idea what the micromagnet field will be, so you adjust it, and that's your story. Yes. Yeah. Was that the same question? Okay, nice. Okay. So given the time, how much? Well, inspecting these radials, the chevron pattern more closely, taking the Fourier transform, you recognize that there are actually 2 resonance conditions. And this then we attributed, and that was not so crazy, to the fact that if you have a low valley splitting, you could populate both to some extent, mostly the lower energy, but to some extent also the higher energy valley state. And depending on which valley is occupied, your G factor will be slightly different. Your G factor is not exactly 2 in silicon, it's renormalized through spin orbit coupling, and in this case also valley orbit coupling. And so, yeah, it will be a bit dependent on which valley is occupied. By rotating our magnetic field and also playing with the gate voltage, we were able to sort of manipulate the separation in frequency between these 2 resonance conditions. We could also take them or make them overlapping, then you get sort of a nicer looking chevron. Of course, if you have to do this for every single quantum dot, that's not practical. So we need something else, which is a large valley splitting. Thank you, Giordano. But at the time, yeah, valley splittings were low and they were a big concern. We were all the time thinking about it. And now we barely speak about it anymore. Well, sometimes we do. Okay, so this is a picture that accompanies the sort of the early silicon efforts with, in particular, Erika and Pasquale. Pasquale and Erika are both still in the field. And Nodar, you also know, I think, yeah, several others. Another picture. Yeah. We also had fun times. Okay, so from now on, I'm going to go a bit more quickly because it starts to be more recent times, and I just want to survey a few more things that we've done. First was a big collaboration with Intel, trying to deliver on this promise that was in the introduction of many papers. Semiconductor qubits are great because you can make them with industrial methods. And so that's what we did. And we could see magnetic resonance. The first data were actually taken here at QuTech on the Intel devices, made really in a mass manufacturing type of clean room. So that was very cool. Anna Maria, who now leads Groove Quantum with Nico, did these experiments. I have to say that the quality was not spectacular. By now it's spectacular, I would say. But okay, this was a first attempt. This was on silicon MOS fins, not on silicon germanium, which they're doing now. We also studied, this is from Menno's group, how we can drive and operate single spins at higher temperatures, hot qubits as warm as a Kelvin, for instance, which is, of course, also important from the point of view of scaling. Can you afford a bit higher temperatures and still operate your qubits? This is a 6-dot linear device, which Stefan Philips and Matthäus Magic operated, and you get quite beautiful Rabi oscillations for each of the 6 spins. They were not taken simultaneously, they were taken one by one, but nonetheless, really quite beautiful. And it's, by this time, things are starting to work more reliably. But we didn't run out of surprises, right? On this device, and we had noticed already on an earlier device, but on this device in particular, what we found, and this is where Brennan spent a lot of time, is that after applying some microwave bursts to manipulate your spins, the qubit resonance frequency would shift. So your resonance starts here, and then as you apply bursts, it drifts. And if you don't adjust, then you're applying your bursts off resonance now, and your control fidelity drops. And it seemed to really depend on the energy that you put in the system. So we started to think of a temperature effect. And at some point, we also raised the mixing temperature to see if that would, lead to a change in the qubit frequency. This was also really fun and exploratory because, I remember we thought about how, let's change the temperature, but by how much, by 1 millikelvin or 10 or 100? When are we going to see an effect? Well, okay, so the answer is here, right? We didn't know, but the answer is here. And what is really peculiar is that the resonance frequency initially shifts one way before sort of plateauing and then coming down. And that was seen on all of the spins. So here you see measurements on 4 spins. And even now, we aren't fully sure of the explanation. So Brennan and others have looked back at this question on other samples. And what you hope typically by looking at more samples is that you can get a more complete and consistent understanding. And it's been, in this case, almost the opposite. Like there are samples where, for instance, the frequency shift with driving was opposite to the frequency shift with temperature. So, okay, you thought you understood something, and okay. So, and it's still not completely clear, but what is clear is that it's not a universal effect, which is good. It's seen also in other groups, but not in all other groups. And some groups see it in some categories of devices and not in others. And so that's something that is, of course, informative and that we need to digest further and draw conclusions, because this heating effect makes it really complicated to operate. The qubit frequency depends on what you've done before. Okay, that's a mess. Something else that could be a mess, but it doesn't have to be, is that we started to see nonlinear effects. If you drive your qubit too hard with electric dipole spin resonance, at some point the Rabi frequency no longer varies linearly. It plateaus. It has this sort of funky behavior. We always check whether used to check whether we are indeed driving spin resonance by looking for a linear relationship between Rabi frequency and drive amplitude. And here it's nonlinear. It's not unexpected, actually, right? If you think about it. So there's an electron confined in a quantum dot, and the EDSR mechanism depends on how far you displace your electron in a simple picture. And if you drive harder, at some point, it's not going to move farther anymore because you've already reached the boundary of the dot, so to speak. And yeah, I mean, if you drive too hard, you'll kick it out entirely. But that's before you do that, already there can be some saturation. We also discovered later that there are some instrument contributions to this saturation. So this is good for everybody to know if you don't know already. Your microwave source with the IQ controlled by an arbitrary waveform generator will not produce a linear output amplitude in the IQ. That also shows some saturation at some point. Okay, so like I said, I'm going through more quickly through the recent years, as I announced. This is from 5 years ago now, Corona times. We were still able to go kayaking together at a safe distance from each other. And the faces start to look familiar now. Let's see, I'm running out of time. But the last phase is that we also began to manipulate spins not just by applying a drive, but by displacing the electron in several ways. And the idea, you could imagine this can be useful, right? Because I just explained that with a drive in a single quantum dot, there is only so far you can displace the electron, and therefore only so quickly you can drive the spin. Simplified pictures, admittedly. What if you take an electron and using the conveyors, which we've been developing in recent years, displacing it over a much larger distance, then you can sample a much larger field gradient. And it's remarkable how well this has been working. I've said it before that as a group leader or as a scientist in general, you learn to accept that things take longer than you think and they don't work as well as you hope. And here it's been almost the opposite. So many things that Jutta and Maxime have gone remarkably quickly, including this. Although also I'm skipping the puzzles. You remember all the puzzles with the higher harmonics and so on. In the beginning, it was also really unclear what was going on, but eventually we got this to work. And then, very beautiful, back to the old Loss de Vincenzo idea, which strangely I had not internalized somehow. Coming from NMR, if there is a spin, you're going to apply a resonant drive. But Loss de Vincenzo said, no, you can just displace your electron abruptly by 2 positions where the local magnetic field has a different quantization axis. And so Menno's group demonstrated this beautifully in germanium, where the G tensor depends on the quantum dot specifics. And so you can use this concept to go back and forth a few times and drive extremely high fidelity single qubit gates over arbitrary axes and angles. And we did this as well with Florian and Brennan in the field gradient of a micromagnet, where the field gradient, well, I'm going to skip the details. Okay, that worked. And then lastly, if you have a field gradient, what you can also do is then use this hopping method, but now hopping controlled by conveyor, not between two dots. So you abruptly go here, rotate around that axis, come back, rotate around this axis. So same concept, but now controlled by the conveyor, and also that works. And what's cute is that depending on how fast you go, your effective rotation axis can be manipulated. If you go fully diabatic, then you get a rotation about this quantization axis. But if you go a little bit adiabatic, your effective rotation axis is less tilted. And so we could use this and again get high fidelity operations. Last data I'll show, not from our group, but from current postdoc Yixin, when he was with the Tarucha group, pushing the fidelity of single qubit control in silicon quantum dots really to very high values. So look at the infidelities. So this is pushing 5 nines. And what it took is a really careful look at everything that could go wrong, applying shaped pulses. Even for a single spin, it makes a difference. I had no idea that this was going to be the case, but Yixin understood why. There were microwave-induced phases still that they compensated for. The Rabi frequency, of course, you have to optimize. In this device, they had reduced heating effects, so that, of course, was important. Oh yeah, and then I thought the last data, well, there was the last single spin data to finish. Kenji and Irene cooled down a device aiming to go back to the good old ESR, but then in silicon. And there's lots to say about that as well. But one surprise is that now we can actually resonantly drive the valley. We had not expected that. But after all, in these cleaner, more modern devices, it can be driven resonantly. These are chevrons of the 2 valley qubits. And this actually inspired, I think it was Kenji or Irene, to think big. Silicon Valley qubits. And I'll have some more group pictures. So summarizing, right? What I've covered is basically in some detail the gallium arsenide days, where mostly we learned how to deliver the control signals, well, isolate single spins, deliver the control, and the physics of hyperfine and spin orbit and how that played out. Moving to silicon, we had to understand how valleys impact things. We had unexpected heating effects, many other things that we learned. And then the last evolution of the last couple of years really is that we can control spins not only by applying a drive, external drive, magnetic or electric, but also by just displacing the electron gradually or making it hop between 2 sites. And that's a novel concept that perhaps will change the field completely for how we do things in the future. All right, so this was the question that I started with. And so what is the answer now? Well, it's in fact pretty easy, right? If you can isolate and measure a single spin, know how to deliver the control, and you know your system in full detail. Does it sound easy to you? I don't know. It's still not completely routine, although most of the times I think we see single spin resonance pretty quickly these days. But you could also ask, how interesting is it? And this has been completely beyond anything that I expected. 25 years ago when we started to work with Leo on this project, that there would be so much rich physics coming up in the 25 years that would follow. I had really not anticipated, and that's been really fun. We learned about how to manipulate the spins, about how to, about their coherence and the decoherence mechanisms and so on. Of course, also how to scale. And so what also I find really interesting is that even in very recent years, we're discovering new ways of controlling the spin. So we have not run out of new ideas for rotating single spins. And I'll end with this statement. These surprises have been really fun to think about. They've been puzzles, and you can come to an understanding and feel good about the understanding you developed as a community. But of course, eventually, I hope that we will leave the surprises behind us, and that it's going to become boring. And when it will be boring, maybe it will be ready for the technology. So thank you. I'll end here.
talk. I think we have time for maybe 1 or 2 questions, depending on how lengthy the questions are.
Thanks for the very nice talk. I was wondering, so in a single quantum dot, like, can you also make the position of that dot some quantum mechanical variable? Like, I think of a harmonic oscillator. I have a position variable Q that I can write information in. Are you thinking about this?
So yeah, this is a possibility, and it's actually been tested first by Fujisawa at NTT, and you can encode the position. For instance, you can have an electron in the left dot or in the right dot. That's a 0 and a 1. It works. The coherence is very short-lived, and so yeah, the dynamics is also very fast. But altogether, the spin seems to offer a better trade-off, and that's what everybody pretty much is doing.
Thanks a lot, Lieven. As a person who's been spending many years hunting for the first single spin qubit, what advice would you give to people hunting for novel types of qubits, but in 2026?
Yeah, so I mean, one very generic advice I would say is always follow your interests. If there's something that you're really enthusiastic about and keen and that you find interesting, go for it and count on it that others will also find it interesting. And be open-minded. Yeah, be in an exploratory mood. Be ready to discover. I think if you from the beginning have too much of an engineering mindset, you lose out on a lot. Of course, our entire field, in a way, is in an engineering mindset. We're trying to achieve a technology ultimately, or lay the foundation for it. But our role as scientists is, to lay that foundation. And if you're not sufficiently open-minded, you'll, miss many opportunities.
And I think the last question looks like it's a good online question to wrap up, which is, will you write all of this down?
Yeah, maybe when I'm retired. I'm not sure yet. It's actually, I've been thinking also about a review article or so maybe, but yeah, I'm not sure if I'm at right now sufficiently motivated next to all the other things that I also like to do. But yeah.
Great. Then thank you. Yes. Let's thank Lieven again.
Thank you all.